Alright, now we're going to talk about how gravity affects pressure. So, the way that we think about this, the change in pressure, and I should probably do a capital P here, is the original pressure you start with plus density times gravity times height. Looking at this is a lot like potential energy. Normally it's mass times gravity times height, but it is actually the reason why it looks the same. It is the potential energy, basically, of a fluid. Okay, so the other way you can also think of this over here is the pressure at the bottom, which will be greater, minus the pressure at the top. Okay, so for example, the book explains that there was a group of people in the Navy in the 1960s that went to the bottom of the Marianas Trench. They said that this trench is actually 10,700 meters underwater. And if you floated down to the bottom of a pool, you notice there is a lot of a lot of pressure from the water above you, and it can be rather uncomfortable. So that's only like 12 feet. This is 10,700 meters. And they wanted to know if they have a window that is exactly 1 centimeter squared in area, then what is the amount of force or pressure being pushed against that window? And so what we're going to do here is we're going to see that the change in pressure is going to be our original atmospheric pressure plus rho GH. Now, one thing about this is we need to be careful here. Do we want the total pressure or do we just want the change in pressure? And I want the change in pressure, which means that we're going to leave off the initial pressure you feel from the atmosphere. Okay, now we need to put in density, we need to put in gravity, and we need to put in the height that we've changed. So the change in P is going to be the density of salt water. The density of salt water is 1,029 kilograms per meters cubed. Now how's that different from normal water? Normal water is supposed to be, in perfect conditions, 1,000 kilograms per meters cubed. So it's slightly denser than normal pure water. So that will be our first 1,029 times gravity, which is 9.8, times how many meters we went down? 10,700 meters. All right, so we multiply that out on our calculator. And I'm getting a large number. The change in pressure is 1079.00940. Now we have 3 sig figs, so I'm going to just round it to here and move the decimal over 1, 2, 3, 4, 5, 6, 7, 8. So our pressure is 1.08 times 10 to the 8th pascals. Now the question, we want to know how much force is being exerted on that window. Remember, force equals pressure times the area. So, if we want to find the force, we have to take this pressure, which is 1.08 times 10 to the 8th. We have to times by the area. But we have to do a little bit of work for the area here because we want meters. And right now they gave us 1 centimeter cubed. Okay, so I'm going to go back to what we did in the very beginning of the course. 1 centimeter. If this is a 1 centimeter by 1 centimeter cubed, that'd be the same as 0.01 meters by 0.01 meters. So when I think about the area there, that would be 0.01 times 0.01, which is 0.0001 meters. So for my area, that's what I'm going to use, which you could say is 1, 2, 3, 4. That'd be 1 times 10 to the negative 4. Alright, so our force here is going to be 1.08 times 1 is 1.08 still. And this is going to be times 10 to the 4th. 1, 2, 3, 4. So fourth is 10,800 newtons. I divide by 4.45, that'd be 2,430 about pounds of force on that small little window. So this also explains why, if you increase the area, you're going to be increasing the total force of that pressure. So this is an explanation why submarines will have small windows, basically. Okay, so I would like you to try something. We just want to know what is the pressure increase going 12 feet in a pool. So now would be the time to pause the video, try it out, and then come back to see. Okay, so change in pressure equals the initial pressure plus rho GH. So we're only looking at the change, which means I'm going to get rid of the pressure at the top of the pool, and I'm simply going to do the change in pressure times the density times GH. Now, if you were listening, the density of water under just pure water, so let's assume it's just pure water, is about 1,000. This would be 9.8. And we have to take 12 feet and transfer that into meters, which I looked up, it is 3.66 meters. So we'll put 3.66 there. Multiply it out. And we're going to get a change in pressure, which is about 35,868. So with sig figs, we would say 35,000 newtons. Now, it would be nice to figure out how much force that is, but to figure out force, we need to have the area, the cross-sectional area. So what we could do, we found the pressure change. Sorry, this isn't newtons, this is in pascals. We found the pressure change. We could do force equals pressure times area and figure that out. And one way to think about it is, what is the area of your eardrum? That is going to be an extremely small area. So even though the pressure increase is very large and we can feel it, the area of our eardrum is so small that when we calculate the force, it actually compensates a little bit. So that's why we're not feeling that full feeling of 35,000 Pascal change in pressure. Okay, so there's some more examples here. We have this setup, which is very common. We have this tube that's kind of bending around. Now on one side we have one liquid, and on the other side we have oil poured in the top so that the liquid actually is pushed down on the right side. If you think about it, the atmospheric pressure on both sides is the same and would cancel out. So we have this water that has a certain height. The key here to think about is I have this point and this point. So even though I'm putting oil in the top here, and because it's a certain density, it's lighter than water, but because it's a certain weight, it's going to be pushing the water down and up on the other side. But the pressure here and the pressure here have to be the same because it's in equilibrium. So think of this as your height 1, and think of this over here, which my drawing is not that good, but this height 2 is much larger. So if this is oil and this is water, and we know that H1 is 0.1 meters, the question is, how much is H2 moving up? And then you could see what is the difference in the heights. So I guess the real question is, what is the difference in heights? Okay, so let's write this out with what we know so far. The pressure at point A and point B are the same. And now normally we would write the pressure of the atmosphere plus rho GH equals the pressure of the atmosphere equals rho GH. Sorry, that should be a plus sign over there. But the atmosphere is the same on both sides. So really this is rho GH1 equals the row of the oil, G times H2. Because from point B upward we have only oil, and over here this should be the row of the water, so I'm going to put row of water right there. So we're comparing the height of water and the height of oil here only. Now, if we plug in, or if we want to find the difference, I'll write this over here. The difference in heights is H1 minus H2. So over here, what I'm going to do is get H1 alone. So this is going to be, I can cancel out the g's on both sides, and I'll divide by the row of water. So H1 is the same as row of oil divided by the row of water times H2. Now instead of writing H over here, I can rewrite it as this. And I'm sorry, I made a mistake here. H2 is taller, so I need to write that first. H2 minus H1. So instead of H1, I'm going to substitute in. So the difference is going to be H2 minus row of oil over the row of water times H2. Now if I factor in H2 out to the front, H2 is going to be 1 minus the row of oil all over the row of water. Alright, and now, unfortunately, I told you that this is H1. This is actually H2 up here. So sorry about that. We have H2, and we're trying to find the height of how much the water would go up over here. So, plugging things in here, let's say the oil has a row of 700. We would write H2, which is 0.1 times 1 minus 700 all over 1,000. And that will get us the difference, which is going to be 0.030 meters, or about 3 centimeters. Okay, so the main issue here, that was kind of scattered here. The main issue is that at this point where there's a separation, up here you have only oil, up here you have only water, and their pressures are the same at that point. So use that fact to write out the difference, and then write out the different pressures equal to each other to figure out a problem like this. So really quickly, there's one other thing here, and actually I'm running out of time on my recording software, so I'm going to make one more movie.